Calc Chapter 24. Today we're going to be kind of diving into improper integrals. We're not going to be exactly solving them yet today, but we're going to learn about two rules, L'Hopital's rule and then partial fraction decomposition, which are going to help us with improper integrals. So L'Hopital, he's French, which is why we don't pronounce the S in his name, but he was a man that realized some of our limits come up as 0 over 0 or indeterminate forms. And so his rule helps us evaluate limits that end up turning into indeterminate forms. And so as long as we have these functions, f of a equals g of a, and they're equal to 0, and that the derivatives of f and g at a exist, and that the derivative of g of a is not 0, then we can say that the limit as x approaches a of f of x over g of x equals f prime of a over g prime of a. So this is taking it way back to limits, but it's going to help us, again, with those improper integrals. So this is kind of how we can see it falling into place. So I'm asked to evaluate the limit as x approaches 0. And so my first instinct is to just plug in 0. So I'm going to plug in 0 to get the limit x approaches 0 is 1 plus 0 minus 1 over 0. And this ends up being square root of 1 is 1, 1 minus 1 is 0 over 0. So this tells me that I need to use L'Hopital's rule. And so what we're going to do is we're going to rewrite the top and bottom into their derivative forms. So I'm going to say the limit as x approaches 0. I'm going to take the derivative of the top, and I'm going to rewrite this as 1 plus x to the 1/2. So I take 1/2 times 1 plus x to the negative 1/2 minus, that goes away. The derivative of 1 is 0, and the derivative of x is just 1. And so now I have something that I can kind of work with. So then when I plug in 0 here, I get 1/2 1 plus 0 to the negative 1/2, and this ends up being 1/2 times 1 plus 0 to the negative 1/2 looks like 1 over 1. So this ends up just being 1/2. So this is kind of how we see L'Hopital's rule come into place. I evaluate it, I get an indeterminate form. When I take the derivative, I get an actual number. And this can work. You might have to take the derivative multiple times, but it will should end up working. However, sometimes we end up with functions that we still have 0 over 0 for the derivative. And so we have this stronger rule that we use in that case. And so in this case, the main difference between this one and the last one is that we can take the limit as x approaches a of the derivatives. We don't actually necessarily have to evaluate it at that point. So we're going to kind of see what this looks like with a different function. So again, when I try to evaluate this limit, as x approaches 0, 1 plus 0 minus 1 minus 0 over 2, all over 0 squared, we end up again with 0 over 0. So now I look to L'Hopital's rule. And so I try to take the derivative, so limit as x approaches 0. This derivative is again 1/2 1 plus x to the negative 1/2. Derivative of 1 is 0, and then the derivative of x over 2 is 1/2, all over the derivative of x squared is 2x. And so this isn't working out, again, because if I plug in 0 here, I get 1/2 I get 1/2 minus 1/2 over 0, and that's still 0 over 0. So again, we can't really take this limit because it still doesn't exist. So what I'm going to do is I'm actually going to do it again. And I'm going to take the second derivative. So I'm going to end up with negative 1/4, 1 plus x to the negative 3/2 all over 2. And now that I have that x out of the denominator, that looks something like I can evaluate. So I'm going to take this limit, and I should get 1/4, 1 plus 0, negative 3/2 all over 2. And what I end up with, when I simplify this, I should end up with negative 1/8. So that is what our limit ends up being equal to. And again, we can do this however many times it takes us to get to a point where we can actually plug in whatever limit we're taking. So the next big idea we're going to cover, and this is a very BC topic, is partial fraction decomposition. And if you take a math in college, this is something that you're going to come across, especially with linear algebra and differential equations. So partial fraction decomposition. So it's kind of moving backwards from what we're given here. So what we're given here is we're given two fractions. We want to combine them. They have different denominators. So I would multiply this first one by x over x, and I multiply this second one by x plus 3 over x plus 3. So what I would get is x squared plus x plus 3 all over x squared plus 3x. And so with partial fraction decomposition, my goal is to get from here and go backwards. So we're given the final product, and we need to go backwards. And we're going to see this especially with integrals, because I can't integrate something like this, but I can definitely integrate this top part. So that's kind of why we cover this. So how we're going to do this, this honestly just requires a lot of practice when it comes to partial fractions. And so my first move is I'm asked to write this as a sum of rational functions with linear denominators, so I know that x squared, I don't like that x squared. So the first thing I want to do is I'm going to factor this bottom part. And so I'm going to say, okay, what multiplies to 2 times 3, multiplies 6, adds to negative 7. When we factor this, it should look like 2x squared minus 6x minus x plus 3. Take a 2 out, x minus 3. Take a negative 1 out, x minus 3. So my bottom looks like, my top looks like x minus 13, and my bottom looks like 2x minus 1, x minus 3. And so the two factors that I'm going to try to split this into is something over 2x minus 1 and something over x minus 3. So we generally write big A, 2x minus 1, plus big B, x minus 3. And so I know that if I, let's say, started in this step, just like in the last step, I would multiply, I'm going to use different colors. I would multiply the green fraction by x minus 3, and I would multiply the blue fraction by 2x minus 1. So this is kind of how I'm going to write this. So x minus 13 over 2x minus 1, x minus 3 equals a times x minus 3 plus b times 2x minus 1 all over 2x minus 1 times x minus 3. So this is just more of an abstract way of what we did in the last slide. And so now I have the same denominator, so I know that these top portions are equal. And so I can say x minus 13 equals a x minus 3 plus b 2x minus 1. So now I have an equation with kind of 3 variables going on. And so I notice that there's 2x values that will help me kind of solve this. And so if I set x equal to 3, that will get rid of this a component, and then I could solve for b. And if I set x equal to 1/2, this would get rid of the b component, and I could solve for b. So I'm going to plug in 3 and 1/2, and I'm going to see what each of them equal. And the important thing to remember is that you plug in 3 and 1/2 everywhere you see x. So let's start with x equals 3. So when I plug in x equals 3, I get 3 minus 13 equals a 3 minus 3 plus b, this is 6 minus 1. So I should get negative 10 equals, this becomes 0. So I get 5b, and so I should get b equals negative 2. So I found b. Now I'm going to plug in 1/2. X equals 1/2. So I'm going to take 1/2 minus 13 equals a times 1/2 minus 3 plus b times 1/2 times 2 is 1 minus 1 equals 0. So that one cancels out. Here I should get negative 12.5. I'm going to write this as a fraction, negative 25 over 2. And then here I should get negative 2.5. Again, I'm going to write that as a fraction, negative 5.5 halves a. And if I divide both sides by 5 halves, this gets a little messy, but we can still solve for it. And I should, well, let's not divide. Let's multiply by the reciprocal. So if I multiply by the reciprocal, these 2's cancel out. And we're left with 5, so a equals 5. So my final product, I would say x minus 13 all over 2x squared minus 7x plus, not 6, plus 3. Oh, that's an eraser. Plus 3 equals 5 over 2x minus 1 plus negative 2 over x minus 3. Just going back to our original up here and subbing in for a and b. And so really it's just moving backwards from simplifying, and we should get something that looks like this. So now I have a DIY problem for you. So try to simplify this into 2 fractions, just like we did in the previous ones. The denominator should have linear factors. So go ahead, pause the video, write this down, and then try it yourself. So this is the answer you should get. So here's kind of the steps, how to separate them, and then how to go from there. So please make sure you kind of can understand this. You can do a few problems on this and come to class with any questions you have. I know it's a long break. Just please kind of keep math in the back of your head. Let me know if you have any questions. You can email me over break. I will respond. And please make sure that you like and subscribe. And thanks for watching.